Hey, this is Nicholas. I got a really good article you guys are gonna like. It's gonna explain basically what we've been talking about this whole time: transfer of energy, um, pre-sequels, precursors to big earthquakes and stuff like that that we see in the Blot echo, the TEC data. They're finally realizing what we've known for a while. So here we go. How earthquakes deform gravity. This is from Helmholtz Association of German Research Centers, and this is basically like a image of spatial distribution of peg signal strength during the Tahoe quake. So that's just an example. Lightning 1, 2, 3, and thunder. For centuries, people have estimated the distance of a thunderstorm from the time between lightning and thunder. The greater the time gap between those two signals, the further away the observer is from the location of the lightning. This is because lightning propagates at the speed of light with almost no time delay, while thunder propagates at the much slower speed of sound of around 340 meters per second. Earthquakes also send out signals that propagate at the speed of light, 300,000 kilometers per second, and can be recorded long before the relatively slow seismic waves, about 8 kilometers per second. However, the signals that travel at the speed of light are not lightning bolts, but sudden changes in gravity caused by a shift in the Earth's internal mass. Only recently, these so-called pegs, which is basically prompt elastogravity signals, were detected by the seismic measurements. With the help of these signals, it might be possible to detect an earthquake very early before the arrival of the destructive earthquake or tsunami waves. However, the gravitational effect of this phenomenon is very small. It amounts to less than 1/1,000,000th of Earth's gravity. Therefore, peg signals could only be recorded for the strongest earthquakes. In addition, the process of their generation is complex. They are not only generated directly at the source of the earthquake, but also continuously as the earthquake waves propagate through the Earth's interior. This is the transfer of energy, guys. This is the antipodes that we talk about. The earthquake waves, they go through the Earth's interior. So you're going to get those transfer of energies. Until now, there has been no direct and exact method to reliably simulate the generation of peg signals in the computer. The algorithm now proposed by the GFZ researchers around Rongyang Wang can calculate peg signals with high accuracy and without much effort for the first time. The researchers were also able to show that the signals allow conclusions to be drawn about the strength, duration, and mechanism of very large earthquakes. The study was published in the journal Earth and Planetary Science Letters. An earthquake shifts the rock slabs in the Earth's interior abruptly and thus changes the mass distribution in the Earth. In strong earthquakes, this displacement can amount to several meters. Since the gravity that can be measured locally depends on mass distribution in the vicinity of the measuring point, every earthquake generates a small but immediate change in gravity. However, every earthquake also generates waves in the Earth itself, which in turn change the density of rocks and thus the gravitation of a little bit for a short time. The Earth's gravity oscillates to some extent in sync with the earthquake. Furthermore, this oscillating gravity produces a short-term force effect on the rock, which in turn triggers secondary seismic waves. Some of these gravitationally triggered secondary seismic waves can be observed even before the arrival of the primary seismic waves. So this is the P waves. The P waves are the primary waves. That's the first waves coming from an earthquake. The secondary seismic waves are those S waves that we talk about. We face the problem of integrating these multiple interactions to make more accurate estimates and predictions about the strength of the signals, says Torsten Dahm, head of the section Physics of Earthquakes and Volcanoes at GFZ. Rongyang Wang had the ingenious idea of adapting an algorithm we had developed earlier to the PEGS problem and succeeded. We first applied our new algorithm to the Tahoe quake off Japan in 2011, which was also cause of the Fukushima tsunami, says Sebastian Hyman, program developer and data analyst at GFZ. Their measurements on the strength of the peg signals were already available. The consistency was perfect. This gave us certainty for the prediction of other earthquakes and the potential of the signals for new applications in the future by evaluating the changes in the gravity many hundreds of kilometers away from the epicenter of an earthquake off the coast. This method could be used to determine, even during the earthquake itself, whether a strong earthquake is involved that could trigger a tsunami, according to the researchers. However, there is still a long ways to go. Today's measuring instruments are not sensitive enough, and the environmentally induced interference signals are too great for the PEG signals to be directly integrated into a functioning tsunami early warning system. So I'll put the link in the description. This is very good news, guys. They're finally realizing that the earthquakes give signals from gravity. This is amazing. I mean, this is basically what we've been talking about this whole time. Wow, okay. Sorry that earthquake alert keeps coming up for the Philippines. But yeah, this is amazing. We've been talking about this transfer of energy. We've been talking about the S waves, the P waves, the antipodes, and all this. So there it is, guys. I'm going to put it in the link. Please like and subscribe to our videos. Share them. Because this is going to help everybody out. You know, you're going to see things the way why we do things on the page. So thank you for listening, and God bless.